Welcome back. We're now going to be talking about modular arithmetic and multiplication. So in the first half of the lecture, we talked a lot about how do you do modular addition and subtraction, and somehow it wasn't very surprising, right? You basically just do ordinary addition and subtraction, and then you divide by 5 and take the remainder, and that gives you everything. And so in some ways, that's not too surprising, and you might be asking, well, why did we go to all this work to invent these new kinds of numbers when they behave very, very similarly to your old kinds of numbers, except they somehow wrap around? Well, the answer to that is when you're dealing with addition and subtraction, that's easy. But when you start dealing with multiplication and more complicated functions, then all of a sudden things are different. And just a reminder, when you have this clock arithmetic, which is what we've been dealing with, clock arithmetic and modular arithmetic mean the same thing. There's different names for the same thing. And I will be using both interchangeably. So as we discussed, addition can be thought of as clockwise steps around a circular number line. And subtraction can be viewed as counterclockwise steps around a circular number line. And of course, so basically the idea is somehow we're thinking of wrapping the infinite number line around the circle many times. So if you have your circle, basically what we're doing is we're taking the ordinary number line and we're wrapping it around many, many times, right? So that's the basic idea behind what we're doing. Let's take a moment and talk a little bit about math history. So someone had to invent these things, right? So like all kinds of numbers we would talk about were invented. So for example, let's go back and review our big slide. You do not need to memorize dates. You do not need to memorize the dates of this on the midterm. Let me just say that several times. But you should have some general sense of these things because I think it's cool. So negative numbers were invented around 200 to 200 BC to 200 AD. Multiplication was invented a long time ago, around 4000 BC. Direct division around 1500 BC. Irrational numbers were invented around 500 BC. But then complex numbers were only invented around 1545. Well, the big question that someone else, well, I messed up my slide. So I didn't turn on the animation. But yeah, so I will, so you don't need to bother answering, but the answer is it was invented. You can go ahead and answer if you want. I'll go ahead and let you have this free participation mark. But yeah, so the modular arithmetic was invented in 1801, so just barely the 1800s by Carl Friedrich Gauss, who is one of the titans of like 1800s mathematics. And it's only barely in the 1800s since the book that the treatise that he published was only in 1801, so barely the 1800s. But this is one of the most recent types of numbers that mathematicians have invented. And so we're starting to get into much more modern stuff. And so we're going to get pretty close to the current day in the grand scheme of things, right? So like 200 years ago, that's still a long time ago, but it's not like 6,000 years ago, a long time ago now. Do we have to know the history? No, you don't have to know the history, but I think it's cool stuff. And I'm hoping some other people think it's cool as well, so. Okay, but anyway, so for today, we're going to, actually go through and derive multiplication. Something went horrendously wrong with my slides. I don't know what's going on here. So I am very confused by what's going on. Anyway, so we can think of multiplication as repeated addition. So that's when I would have written out this line, because 4 plus 4 is equivalent to 8, which in mod 5 is equivalent to 3. So that's mod 5. I don't know why some of my writing is disappearing, some still there. But what does it really mean to multiply by a number in modular arithmetic? So, well, you might think, well, maybe we can do the same thing. Maybe you can just multiply and then take mod 5 and find the remainder, and that gives you the answer that you want. So note that 2 is equivalent to 7 mod 5, but now you have to worry a little bit, right? So somehow when you were adding numbers together, you didn't have to worry about adding 2 or adding 7, because when you add the 5 in there, that's just equal to 0. But what about is 2 times 4 the same as 7 times 4? And if so, so is that the case in this particular case? And is that true in general? So can you just multiply by either 2 or 7 and get the same answer? It somehow seems a little bit odd that you could multiply like 2 times something and say 222 times something would give you the same answer. So is that true or is that not? So a lot of people are guessing no. And this is a real question that you should be asking yourself. Like somehow it makes sense that if you add numbers that are multiples of 5, those give you 0. But why would it also be true that you could multiply 2 and 7 and get the same answer? Well, but then you have to look a little bit, and you're like, well, wait a moment. There's someone who asked, it depends on what the other number is. But look here, I did actually do 2 times 4 and 7 times 4. And you do get the same answer. This seems a little bit odd, right? And part of this is, of course, the magic of modular arithmetic, that you can do this. And so somehow, even though, and it really depends on how you're thinking about things. So in this modular arithmetic system, multiplying by 2 and multiplying by 7 in mod 5 arithmetic are actually the same thing. There are same points along there, and that is something we do need to show. Because really, look, sorry, my slides are all kinds of messed up today. Something went wrong. But anyway, so the question is, are you repeating the addition 2 times or 7 times? And of course, that seems like it ought to make a difference, right? Because if you think about the number line, so that's 0, 1, 2, 3, 4. Well, repeating 2 times, well, that's 1, 2, 3, 4, 1, 2, 3, 4. You end up at 3. But then if you are going to do it another 7 times, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, you just keep on going around, and eventually, why do you end up back at 3? So does anyone have an idea about how we're going to prove this? So if you do, feel free to throw it in chat. But it is actually true that, well, I am doing, so which of these should we do? Which of these is the right thing to do? Repeating it 2 times or repeating it 7 times? Okay, yeah, well, I sort of gave away the answer because my slides are not in the right order today. But yeah, the answer is yes, you're doing both. Both are accurate. Doing it 2 times and doing it 7 times are exactly the same. And there is a reason for this. So let's actually see this in this particular example. And that is that 7 times 4, well, what is that equivalent to? Well, you might notice that that's equivalent to 5 plus 2 times 4, right? But 5 is equivalent to 0, so that's equivalent to 0 plus. Actually, let me do it out the other way first. So that's equivalent to, we can use the distributive property, which we haven't proved yet for all of this, but it is, you can prove it the same way, which we're going to do in a moment. 5 times 4 plus 2 times 4, right? But what's 5 times 4? Well, 5 times 4 is equivalent to 0 times 4 plus 2 times 4, which is equal to 8, which is equivalent to 3. So somehow, doing 5 times of anything is just going to be 0, right? Because 5 times anything is a multiple of 5. And so that part's going to be equal to 0. And so it is, so repeating addition 2 times and repeating it 7 times doesn't make a difference. Okay, but let's go ahead and prove the distributive law, because that's what we just used there, right? So somehow we've invented multiplication as this repeated addition, and then the question is, do we still have the same kind of distributive law that we did back in ordinary arithmetic? And the answer to that is, well, yes, we do. And let's prove it. And so, well, left-hand side, so listing here, says go clockwise by jumps of a total of b plus c times, right? So that's what the left-hand side is saying. So we're saying we're jumping in steps of a, and you're doing it b plus c times. So if we draw that out, because we are going around the circle, right? So we don't know how many different spaces there are because we don't know, this is just mod n, so there could be any number of these, but you're going right around, clockwise around this in jumps of size a total of b plus c times. Well, what is the right-hand side? The right-hand side says to go clockwise by jumps of a b times, then you do another set, go clockwise by jumps of a c times. Okay, so really it's the same thing. So it's either you go b plus c jumps of a, or you go b jumps of a and then you go c jumps of a. And so clearly the distributive property still holds here. And we also have another important fact. So if you're in mod n, going n jumps of any size a always returns to 0. And why is that? This is actually a consequence of the commutative property. But it's pretty easy to see directly. So n jumps of size a, that's equivalent to a jumps of size n, right? So those two are the same thing. If I go five steps of size 2, 2, 3, 4, 5, versus if I were to like hop over in groups of 5, like those are the same thing. And that's true along the circle, just as it is in, along a flat surface. And so, but notice that in this particular case, a jump of size n is equivalent to a jump of size 0. Because you're jumping all the way around the circle. So that's the same as just jumping in place. So a jumps of size 0, that's still equal to 0. And combining these two, we get the fact that multiplying by 2 or multiplying by 7 in mod 5 are the same thing. And together, these two properties allow us to do fast modular multiplication. So in mod n arithmetic, repeating addition 0 times is the same as repeating addition n times, right? So what you can do is you can have a times b mod n. That's, I needed 3 lines there. That's equivalent to a mod n times b mod n. So let's give an example of that. So 8 times 9 mod 5. So that's equivalent to 72 mod 5, which is equal to 2 mod 5. Right? Okay, so that's easy enough. But you could also do this. That's equivalent to 3 times 4 mod 5, which is equivalent to 12 mod 5, which is equivalent to 2 mod 5. Because you can like reduce both of their original numbers first. And that's also equivalent to 3 times minus 1 mod 5, which is equal to minus 3 mod 5, which is, equivalent to, which is equivalent to 2 mod 5. Because of course 4 is equivalent to minus 1. So just as with addition and subtraction, you can make things easier by converting the interior numbers into other forms when you're going about this. Well, let's try it out. So let's see. So what is 4 times 9? I see someone answered in chat was just ordinary 4 times 9. Well, in this case, we want 4 times 9 in mod 6. Okay, so a lot of people are answering 0, and that is indeed correct. And let's see this. So this is equivalent to 36 mod 6, which is equivalent to 0 mod 6. That's just divisible by 6. Or you could also see this a different way. So, or you have this is equivalent to 4 times 3 mod 6, which is equivalent to 12 mod 6, which is equivalent to 0. And notice, this is actually quite important. 2 non-zero numbers multiplied together to give 0. So this should strike you as a little bit odd, right? Because in ordinary multiplication with ordinary numbers, you can't ever multiply 2 numbers together and get 0. But in modular arithmetic, sometimes you can. And that's something we're going to play around with a lot more later. But I just want to point this out now while we're learning multiplication. Okay, what about this one? 3 times 6. Mod 7. Okay, looks like people are getting 4. Well, this is equivalent to 18 mod 7. And well, 14 is a multiple of that, so that's equivalent to 14 plus 4 mod 7, which is equivalent to 4 mod 7. Oh, wait, let me write this a little bit further up. So that's equivalent to 4 mod 7. Well, let's do something slightly bigger. What about 21 times 39 mod 5? So I would suggest that you try doing this without a calculator. You will be allowed to use a calculator on the exam and quiz, but like it can be helpful to understand how you do these things without calculators, just to get a better sense of like tricks you can use, basically. Especially since you're not, it doesn't count for anything right now. Like obviously on the exam, I would recommend that you double check your answer with a calculator. Okay, looks like people are answering 4. Well, what is the answer? Oh, when do you write the mod number in brackets and when do you not? So the real answer is that if you were going to be completely precise, you would always write the mod number in brackets. Oh, sorry, brackets versus just like writing without the brackets. That's notation. They mean the same thing. So let's, mostly me being lazy at this point. I started defining it by using brackets, but if you have brackets or don't have brackets, that's perfectly acceptable and you will get full credit. As to when you write the mod 7 or mod 5 or mod 6, you do need to write it whenever it's ambiguous. So sometimes you'll see me just write the equivalent sign without the mod at the end. That's usually just when I hope that it'll be unambiguous what number I'm taking the mod of. If it's at all ambiguous, you do need the whatever mod n is. Okay, but what is this? Well, I'm going to claim that this is equivalent to 1 times 4 mod 5. Right? And so that's equivalent to 4 mod 5. Because that's the remainder of each of those individual numbers, and so that's a really fast way of doing it. But now, the other way of doing it is you could multiply these two numbers together, which happens to be 819, which I used the calculator for earlier, mod 5, and you can divide it out, so it's equivalent to 4 mod 5. One of these strategies takes a lot more work. And yes, it might not seem like it takes a lot more work when you have a calculator, but even with a calculator, you will find that there will be problems where trying to do it all in a calculator won't work out so well, and you will have to use these tricks of like substitution to make things smaller before you reduce, before you multiply. Such as with this number. What is the value of this? Oh, and then I'll give you guys another moment or two. So does anyone want to point out the trick? Go for it. Yep. So yes, 0 times anything is equal to 0. So I don't even care what the other thing's equal to. But this is equivalent to 0 times something, which is of course just equal to 0. But notice that even if it were some other number, like for mod 5, it would be easy because you just need to take the remainder and you only need to look at the first digit. Though that's not true for other mods. Like if they did mod 9, then that would be a little bit more difficult. But actually, Actually, that's a good point. Suppose that this was mod 3. What would the answer be? Yeah, the answer would still be 0 if it were mod 3, because if you check, you'll find that the first number is divisible by 3, just by adding all the digits together. And so there's some sense in which using these tricks is super helpful because it means that you don't need to do these really big calculations. And some of these calculations may be too big for you to fit on your calculator. So you won't need to know how to actually do these transformations. And you can't just rely on your calculator for everything. And of course, this is mod 5. Okay, how am I doing on time? 20 minutes, I should be all right. Let's see. How can we multiply by 0 again? Oh, so notice that this number here is divisible by 5. And so if a number is divisible by 5 and you're in mod 5 arithmetic, then that number is equivalent to 0. This is a multiple of 5. Okay, so that's multiplication. And of course, once you have multiplication, well, what's exponentiation? It's just repeated multiplication, right? And so, well, now that we have this, we can write down what we think these things are. So let's give an example, which is, let's see, 4 squared mod 5. Well, that's easy, right? Because that's just 4 times 4 mod 5. 4 times 4 mod 5, which is equivalent to 16 mod 5, which is equivalent to 1 mod 5. And notice, though, that there are a couple different ways you could have done this. So this is also equivalent to minus 1 squared mod 5, because 4 is equivalent to minus 1. Oh, sorry, I don't need to write that. Which then means that this is also equivalent to 1 mod 5. Let's give another example. Let's say we had 2 cubed mod 6. Well, that's equivalent to 8 mod 6, which is equivalent to 2 mod 6. Okay, so whenever you're working with modular arithmetic, you can just do the normal arithmetic and then bring it down. So let's try that out. Let's 0 that. And what's 5 to the 4 mod 6? Okay, so we're getting some answers. I'll wait a moment longer for you all to compute. Might I suggest double checking it a couple different ways if you're already finished and waiting. And remember, this is mod 6, not mod 5. So you always have to watch out for that. Yeah, so it looks like we're getting a couple different responses now. So let's work through this together. Well, one way of doing this is to just multiply this out. So if you happen to have a calculator, or if you happen to have these numbers memorized, well, 5 to the 4th, what does that equal to? Well, that's 625, right? 625 mod 6. Well, then you have to do a division. Well, what's 625 divided by 6? That's 1, 6, 0, 0, 0, 4. That's 24. Sorry, 25, 24, 1, remainder 1. So that's equivalent to 1 mod 6. That's one way of doing it. This is a little bit painful. It's not so painful with the calculator, but you will find that I will be giving you numbers for which your calculator may not be so happy if you try to do it directly. But another way of seeing this is that, or this is equivalent to minus 1 to the 4 mod 6, right? Because 5 is equivalent to minus 1 mod 6. And so if you see that transformation, well, then that makes this a lot easier. So this is just 1 mod 6. Okay, so hopefully you guys are starting to see now how you can use these transformations to make your calculations a lot easier. And yes, using a calculator can make hard things easy, but it can only do so much. Okay, let's have you all try out another one. What is 3 squared? Mod 7. So this one's hopefully a little bit easier. Okay, yeah, so it looks like everyone's, people are answering this one pretty quickly. Well, this is just equivalent to 9 mod 7. When 9 divided by 7, well, what's the remainder? That should be pretty straightforward. That's equivalent to 2 mod 7. And there's no need to do clever tricks because this one's just easy. Okay. Let me give you another one. What about 2 to the 5 mod 5? Let me zero out again. Okay, it looks like people did not fall for the trick. I don't know if that's a good or bad thing, but there was a trick here, which is that 2 to the 5 is not the same as 2 to the 0. So let's first do it correctly. So that is equivalent to 32 mod 5, which is equivalent to 2 mod 5. But note that there is a wrong answer. So let me put it in a box and write wrong around it so you don't. So this is a wrong answer. Don't do this. 2 to the 5 mod 5 equivalent to 2 to the 0 mod 5 is equivalent to 1 mod 5. So this is wrong. So you can't take mod of exponents. Oh, why would you think that the power is 0? You might think that because you know that 5 is equal to 0 in mod 5. But that does not apply to exponents. So somehow the exponentiation is different than multiplication in this way. And so you have to be really careful about that. There are other tricks that we'll eventually learn about how to do modular exponentiation. We have not gotten there yet. And that won't be until after reading week. So I would just be careful about that. So when you take powers, you cannot just use the mod tricks for the powers. You can for multiplication and addition, but you can't for powers. And this is one of the ways in which suddenly modular arithmetic feels different than ordinary arithmetic. I had actually designed that as a sort of trick. I was hoping that you guys would get so used to like doing everything mod 5 that you would make a mistake. But it looks like, yeah, you can't use the modular rules for exponents in that same way. Okay, how am I doing on time? 13 minutes. Okay, but now, okay, so we have the idea of powers now. So that means that we can also have some idea of squaring and cubing and things like that. So now what these exactly mean is slightly different, right? Because, well, you no longer have like actual squares, but you can still have ideas of, is it Halloween in here? Oh, you guys, yes. Well, I forgot to bring the treats today. I'll bring them again after reading week. But yeah, so yes, there will be tricks, and there will occasionally be treats. Which numbers in the let's see. So I'm going to ask another question, which is which numbers in arithmetic mod 5 are squares? And this is pretty easy to figure out. I'm not going to. This is more question we're going to work together. Well, 0 squared is equivalent to 0 mod 5. 1 squared is equivalent to 1 mod 5. 2 squared is equivalent to 4 mod 5. 3 squared is equivalent to 9 mod 5, which is equivalent to 4 mod 5. And 4 squared is equivalent to 16 mod 5, which is equivalent to 1 mod 5. So only 0, 1, and 4 are perfect squares, which maybe isn't so surprising, right? Those are also the only numbers that are squares in the ordinary numbers. But that won't always be the case. And so we'll see that a little bit later. And of course, you can have some idea of square roots because, well, what's the square root of 4? Well, it is 2 and 3, right? And the square root of 1 is equal to 1 and 4. And the square root of 0 is just equal to 0. So notice only some numbers have square roots. Right? The square root of 3 is, is undefined. Okay, and so this should remind you a little bit about just the integers, right? So like not every number has a square root. And we had to define some new numbers if we want square roots of everything. And so somehow we're getting to that point now in modular arithmetic too, where suddenly we're having operations where the numbers aren't defined. And we're not going to define them yet, or I don't actually think we're really going to define them ever for some of these. But we're getting to that point now where you would need to invent some new numbers if you actually wanted square roots. And so for now, we're just going to say the square root of 3 in mod 5 does not exist. Okay, but we also have a sense of powers. And so we can ask another few questions, such as, well, did that make sense when I was talking about squares? That some numbers are squares and some numbers are square roots. Well, we can also talk about things like powers of 2. So what are all the powers of 2? Well, let's write them out. 1, 2, 4, 8, 16, 32, 64, 128, 356, 512, 1024, and so on, right? So you can keep on going. So you have all the powers of 2. Now, what about in mod 11 arithmetic? So I'll give you a moment to think about this because I don't want to just give you the answer immediately. You don't have to reply in chat, but you can if you want to think about it a little bit more. But what are the powers of 2 in mod 11 arithmetic? What does that even mean? Like, what is it? What do I mean when I say powers of 2 in some modular arithmetic? $11 squared. No, because we're talking about powers of 2, not powers of 11. So powers of 2. Divisible by 11, divide by 11. So yeah, so well, you divide by 11. But in some sense, you're doing the same kind of thing, right? So when you're taking powers of 2, each step, you double it, right? And so that's what we're going to do here as well. So we're going to start out with a 1. You're going to double it, you get a 2. You're going to double it, you get a 4. You're going to double that, you get an 8. What happens when I double 8? Yeah. But what else is that equal to in mod 11? Yes. So that's 16, but that's also equivalent to 5. What's next? Anyone? So someone's getting 32. But what would that be if you were to bring it down via mod 11 arithmetic? Yeah, so -1 and 10 are both correct answers. So this goes to 32, but that also goes to 10. And so you could have just doubled 5, because 5 and 16 are the same thing, right? And so if you double 5 or you double 16, they're the same thing. What about the next step? Yeah, so someone's guessing 9. Well, what happens when you double 10? So here we're going to double 10. You could have doubled your 32 to get 64 and done the same thing, but we're going to double 10 here since that's a smaller number and it's a little bit easy to work with. That's 20, but that's equivalent to 9. This is confusing. Yes, this is confusing, which is why I'm going through this slowly. And we will be going through this again. So, but you should, this will be material that you should practice. But yeah, so basically each time we are doubling, because that's what powers of 2 means. It means you keep on multiplying by 2. But remember, each time you multiply by 2, you still need to like take the mod of it and bring it down by 11s. And let's keep on going. So what happens when you double 9? What do you get? What is 9 times 2 in mod 11? Yeah, it's 7. So you notice this is 18. And so that gives you 7. Oh, there was a really good question. Why are we doubling 10 to get 20, but not 5 to get 32? Oh, but you did, right? If you had doubled 5, it would have just given you 10 directly. So sort of the point is when you're dealing with this modular arithmetic, doubling 5 and doubling 16 are the same thing. Does that answer your question? Hopefully that answers that question. Well, let's keep on going. So what's doubling 7? Yeah, so that's 14, which is equivalent to 3. And what's doubling 3? Yeah, it's 6 or -5. And 6 is already one of these numbers. And what's doubling 6? Yeah, so doubling 6 is 12, but that's equivalent to 1. But now wait a moment. Something weird just happened, right? So we just started repeating ourselves because we're back at 1 now. And so we could keep on doubling, but we just get the same chain of things over and over again. So somehow powers of 2 in mod 11 are every number except 0. Okay, because if you look at this, you can check you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you have to be a little bit careful. And you might be asking, well, okay, so that doesn't seem that interesting. If you're in modular arithmetic, you are constantly circling back around, which means that, of course, you're going to hit every number eventually, right? So in the exam, I will specify if I want a positive number. So I will ask you to put it in a simple form. And usually that simple form will also mean I ask you to put it between 0 and 10 or whatever. So I will normally ask you for the positive version. But it still is useful for you to know the negative version because sometimes it's easier to multiply with. What about in mod 9 arithmetic? So what are all the powers? So I am running a little bit out of time. I'll give you a moment. So try to think a little bit about this and try to do it yourself for a moment. There will be a problem on your assignment that does this sort of thing. So actually, I'm running out of time, so I'll just work through it. But there will be a problem on your homework that is this kind of problem. So in mod 9 arithmetic, well, you have 1, 2, 4, 8. What's 8 doubled? That's 16, but that's equivalent to 7. And 7 doubled is 14, which is equivalent to 5. and 5 doubled is 10, which is equivalent to 1, and you've already restarted. So you only got 1, 2, 4, 8, 7, and 5, which isn't all of the numbers. So powers of 2 are not all non-zero, not all non-zero numbers in mod 9. So somehow you don't get the same thing for the different mods. The powers of 2, in one case, the powers of 2 are basically everything, and in the other case, they're not. And these types of questions, are powers of 2 going to give you basically every number? Those are actually very important subtle questions in number theory. And I have one more slide and we'll finish off. So a quick word on division. So when we were doing like when we did like multiplication earlier on, we also did division, right? And we're not going to do that because division is actually super different in some ways than a normal division. So it's in some ways, if you think about modular arithmetic, you already have the sense of division, right? That's how you're getting mods to begin with. You're just taking the remainders of normal integers. But what does it mean to divide within modular arithmetic? So just in chat, while we have another minute or two left, what do you think 1/2 mod 5 ought to be? Should it exist? If it exists, what does it mean to have 1 divided by 2? 2.5. So remember, the only numbers you have are 0, 1, 2, 3, and 4. So are you? So if you're saying 2.5, do you mean should we suggest that you invent new numbers in between them? Is that what you mean? Do you want to invent numbers? You want it to be between numbers? What is division? Like, so I don't mean division as like cutting up a cake, but like you guys are all mathematicians here. What did we invent division as? Why did we invent division? That's what good mathematicians do. Cut cake. I mean, cutting cake is what good people do, but I don't know if it's what good mathematicians do. Quick subtraction. So that's not quite right? Because, I mean, that's one of the things you did with it, but we invented division as a sort of opposite of multiplication, right? And so the goal was to find something that you could multiply by, or sorry, why did you do it in fractions? You invented something you could multiply by so that would be equivalent to division. And I'm going to make a claim here. I'm going to claim that 1/2 is equivalent to 3 mod 5. And yes, this is going to be super weird, but basically because 2 times 3 is equivalent to 1 mod 5. Because you're basically doing the opposite of, you're undoing your multiplication. Don't worry, we'll have an entire lecture on this later. I'm just pointing this out that they're weird. This is where weird stuff really starts happening with modular arithmetic. It's when you start thinking about division. Yeah, so don't worry if I lost you. There will not be division on your midterm or on your assignment. I will go ahead and tell you that. This last slide is basically a teaser, basically pointing out that things get weird. And this is why modular arithmetic is so powerful, is because things are not the same when you start dealing with division, the way they were for addition, subtraction, multiplication. So for the first 3 operations, they all seem to make sense the same way. Division, all bets are off. And with that, I am going to call it a day. I have office hours now, so you can feel free to walk with me back over to the IC building in my office. Otherwise, have a good reading week. Watch out for my Quercus announcements. I'll try to get them out by the end of this week. And try to get some relaxation in before, well, midterm season. So bye, everyone.